Process separation and the use of using an MPU or MMU, memory management unit, or memory protection unit. So in this particular case, what we do is we use the MPU to actually put fences around tasks and memory. So we put a fence in the case of process number 1 here. You put a big fence around all these memory locations and you say these tasks are allowed to access these memory locations, but process 2, if ever it attempts to access variables, if it tries to dereference something in processes one's memory space, then the MPU will catch that and will generate an exception, and the RTOS will process that exception and say, hey, you're not allowed to access memory that belongs to a different process. So we're protecting process 1 tasks and IOs from being accessed from other tasks or other processes. So unfortunately, what happens also here to make things simpler, at least in the case of the Cortex-M MPUs or the memory protection unit, you typically implement the ISRs to have full access to memory. If you don't, it makes it extremely complicated to develop an MPU-based system where ISRs only have access to specific memory locations. It's kind of hard to explain and kind of beyond the scope of this class, but trust me, it makes it a lot more complicated. So user task, one good thing about this is user task cannot access the interrupt controller. They cannot disable interrupts because, for one thing, user tasks run in non-privileged mode. So instead of running with full access, full privileges, when you're implementing a system with MPU, you typically run your task in user mode as opposed to supervisor mode or system mode. So that prevents a whole bunch of things. You cannot disable interrupts. You cannot change the interrupt controller. You cannot change the MPU settings, which would be pretty much devastating if a task says, I'm going to change the MPU because I want to access all this memory location. So not the case. And one of the benefits of using MPU is you could actually detect stack overflows in hardware, so there's no chance of you corrupting any memory because you're able to detect that with the use of the MPU. In the case, of course, with stack overflows in the Cortex ARM-v8M or the Cortex M33 processor, there's a stack limit register which actually gives you protection for stack overflows by having that built into the CPU architecture. So anyway, the MPU configuration consists of setting a process table for each task. So each task basically when it runs, will define the memory boundaries of what memory and IOs it will be allowed to access. Now, of course, if they're all part of the process 1, for example, then all of the task process table would be identical except for one item, and that is the stack overflow detection for each of the tasks will be different for each of those tasks. So a context switch now with an MPU is same thing. We save the CPU and FPU registers on a context switch. We restore the CPU and FPU registers from the new task to run. But because we're using a process table, because it's something that's defined typically in ROM at design time, so the memory layout of what tasks have access to is designed by a system designer that says this process with these tasks only have access to these memory locations. So there's no point of creating this process table in RAM because it's subject to potentially being tampered or having problems associated with that. So anyway, so typically you do that in ROM. So there's no need of saving anything because it just gets pulled in from the process table associated with that task. So each task has its own process table, is what I'm getting at. So an expanded view of what a process table would look like. So I would give access to all of the code. Typically, when you're using MP, you don't really need to protect access to code. You typically need to protect access to RAM. So you want to prevent variables from being tampered from other tasks. You want to prevent stacks from being corrupted by other tasks not belonging to your process. So in that particular case, you would put regions around. So the MPU contains, in the case of the Cortex-M, 8 or 16 regions. Typically, it's 8 regions. So a region is a definition of a memory space that you will say this task has access to. So we'll give access to code space. We will give access potentially to IOs, and number 2 here, IOs. We'll give access to the process variables, so the variables that are associated with all the tasks belonging to that process. So maybe it's a control loop and there's set points, there's gains for PID loops, there's timeouts, there's all kinds of stuff that belongs to that process. So we would actually put a boundary or a region around all process variables, plus if there's a local heap to that process. Now, by local heap, I don't mean a malloc and free, because those are dangerous in embedded systems because of fragmentation issues. So a local heap may just be, I'm going to allocate memory in fixed size memory blocks. So anyway, so one of the region is used for that. Another region is to use, and it's being switched between context switches. Whenever the RTOS switches from one task to the other, it puts a region, it puts a memory protection saying that this particular task is allowed to access code, it's allowed to access the heap, the process variable, its own stack space, and its own IO locations. And then it doesn't have access to the other stacks at all. So it's easy if the stack overflows and goes into stack number 2 in this case, then stack number 3, having a region around the MPU protection or a fence around it will say, hey, you're trying to overflow into task number 2, will generate an MPU exception. So when it comes to stack detection, there's a couple of methods we could use for that. So one of them is to allocate what's called a red zone at the bottom of each task. So here you have your task full stack. This is the size of your stack when you're creating your task. And you decide to dedicate a area of your bottom of stack that says, if ever, so everything is allowed except whenever the stack pointer goes down and tries to attempt a write or a read in this memory location, then we will detect that as a stack overflow. There's some, and the other thing I want to mention is typically is about 32 bytes worth of red zone. Otherwise, you lose a lot of memory. If you make that any bigger, you're giving that space as a stack overflow detection. So I prefer not to use this method because it's very possible that the stack pointer, being that it's sitting right here, upon entry of a function call, actually decides to allocate a large array on the stack. And now the stack pointer jumps over the red zone and starts writing stuff outside of the red zone, which happens to potentially be in the space of another task. So don't like to use this method because it is prone to failing. Okay, so the other method is to wrap around the whole stack with an MPU region. And on the Cortex-M processor, the problem with that is that it requires that you make the size of your stack a power of 2, so 32, 64, 128, 256, and so on. And the alignment of the base address of the stack has to align to the boundary of that size. So if it's a stack size of 1K, it has to line up on a 1K boundary on the address space. So a little bit annoying. So, but I still prefer that. I still prefer that over other methods. Now, the other possibility is you put a region just outside, a huge region outside of the memory space of that task. And whenever your stack flows into anywhere in that region, then you would detect an overflow. So if you're almost at the end of your stack and you start writing into potentially a very large region, way more bigger than just the 32 bytes that I mentioned before, in that particular case, it's a lot easier to detect those situations. So when you're doing process separation, user tasks, like I mentioned, run in non-privileged mode, but to use the RTOS services, so the RTOS has to run in privilege mode, there's a mechanism called an SVC handler or trap handler. So all the user tasks actually invoke the RTOS through a indirect mechanism, if you want, that actually invokes the RTOS through an SVC handler that switches from non-privileged mode to privileged mode. Now, the reason I have it shown like this is because you don't want necessarily all the services to be available to non-privileged code. For example, you don't ever want your non-privileged code to be able to delete a task at runtime, or to delete a semaphore, to delete a mutex, or anything like that. So the SVC handler pulls which service that you want from the RTOS from a table, and you're basically saying, I'm able to do a semaphore post, semaphore pen, but I can't do semaphore delete or semaphore create. That could be something that our RTOS application designer decided to do. Okay, so what happens when you get a fault? So in the case of the Cortex-M, the MPU issues an exception called the mem manage fault. It's an exception handler that your application code will need to take care of. Your embedded system will need to take care of this mem manage fault exception handler. So what is done when the mem access violation is detected? Well, that really greatly depends on the application. Should the RTOS just save information about the offending task? Should it just terminate the task, kill the task? Should it kill the whole process? Should it do a whole bunch of things like that? I recommend that the RTOS should provide a callback function for each task, meaning that if an access violation is detected, the RTOS will give a chance for the task to say, oh, by the way, I'm controlling a motor. If this task ever overflows, or stack ever overflows, if I ever access a memory location I'm not allowed to, but I turn on a motor somehow, and the motor needs to be made sure that it's turned off if I'm going to terminate a task, any task. If the task is controlling a motor, I just turn it on, and then whoops, I get an access violation. Then what I need to do is I need to be able to kill that task. So certainly that's one of the things I highly recommend.